Welcome to Section 2.6, Introduction to Differential Privacy and Synthetic Data. In this lesson, we'll explore two powerful approaches to protecting sensitive information while still enabling valuable analysis. Differential privacy introduces a formal mathematical framework that adds carefully designed noise to data, while synthetic data creates entirely new artificial data sets. And now here are the objectives for this lesson. By the end, you'll understand the core intuition behind differential privacy, explain the role of epsilon as a privacy budget, describe benefits and risks of synthetic data, and recognize trade-offs between utility and protection. So differential privacy. Differential privacy is built on a simple but powerful idea. Protect the contribution of each individual in a dataset. Rather than hiding the data completely, the system adds carefully calibrated noise to outputs. This ensures that whether or not a single individual's data is included, the overall results look nearly the same. A key strength of differential privacy is that it provides formal guarantees even when attackers have access to other external information. It shifts privacy from being about secrecy of raw data to ensuring that the influence of each individual is effectively hidden in the aggregate. The privacy budget, epsilon. At the heart of differential privacy is the parameter epsilon, often called the privacy budget. Think of epsilon as a dial that sets the balance between privacy and accuracy. A small epsilon value means stronger privacy protections, but noisier, less precise outputs. A larger epsilon value reduces the noise, improving accuracy, but weakens privacy. Organizations must decide what level of epsilon aligns with their risk tolerance and regulatory obligations. Importantly, privacy loss is cumulative. Each query consumes part of the budget. This makes careful management of epsilon essential when releasing repeated analysis over the same dataset. So synthetic data. Synthetic data takes a different approach. Instead of hiding individuals within the noise, it generates entirely new artificial records that mimic the patterns of real-world data. This enables safe experimentation, testing, and even training of machine learning models without exposing sensitive personal information. It also supports data sharing across teams or organizations while reducing compliance risk. For industries with limited access to real data, such as healthcare or finance, synthetic data can accelerate innovation. The value lies in its ability to provide realistic datasets without directly revealing actual individual contributions. Synthetic data pitfalls. Despite its promise, synthetic data is not a perfect solution. If the original dataset contains bias, those patterns can be reproduced in the synthetic version, perpetuating unfair outcomes. Naive generation methods may even leak sensitive attributes, particularly if synthetic records too closely resemble real individuals. Additionally, synthetic datasets may not fully capture the complexity of real-world data, leading to reduced accuracy in downstream tasks. This makes validation crucial. Organizations must test whether synthetic data preserves the statistical properties needed for analysis, while ensuring it avoids exposing or replicating sensitive information. Pardon me. So in this lesson, we explored how differential privacy and synthetic data protect individuals while still enabling meaningful analysis. We learned that differential privacy hides individual influence through noise, while with epsilon serving as the privacy budget. Synthetic data allows safe sharing and innovation, though it must be carefully validated to avoid bias or leakage. Both approaches highlight the importance of balancing privacy and utility. That marks the end of this lesson, and thank you for watching. Till next time.